So let's look at some basic gas definitions of macroscopic properties versus microscopic properties. So let's look at the macroscopic. Versus the microscopic. What's happening at the atomic level. So macroscopic properties we know are pressure, usually measured in atmospheres. Keep in mind for pressure, we're looking at 1 atm for conversion is equal 1.013 times 10 to the 5th pascals, which is equal to 760 millimeters of mercury, which is equal to 760 torads, or torrs for short. For the microscopic property that we're looking at, what's happening at the microscopic level when we talk about pressure, we're talking about collision force or frequency. So what determines pressure is the amount of gas molecules colliding with the walls of whatever container that we have, right? And if you think about that collision force or collision frequency, that force is equal to the change in momentum of the particles over the change in time for that collision. So we think of it as that force per cross-sectional area is what we defined as pressure, right? And pressure that we talked here on the microscopic property, that's that force per cross-sectional area that we're talking about. Force exerted by the gas molecules colliding with the side walls of whatever container that you have is giving you that pressure. So the macroscopic property is pressure, but that's exerted on and caused by the microscopic property of collision force or collision frequency, okay? The other macroscopic property that we need to know is volume. Volume, typically in the units of liters, units of conversion. 1 liter is 1,000 milliliters or 1,000 cubic centimeters, or sometimes referred to as cc's, right? You hear that in the hospital all the time. You need so many cc's of something. It's just milliliters, okay? So the macroscopic property is volume. The microscopic property is what we call the mean free path. And realistically, mean free path is just the distance molecules travel before collision. So it's some volume per number of moles that we have in between. So it's the mean free path is just the space in between the molecules. So it's the distance that one molecule has to travel before it collides with another molecule. Really just saying that that's the distance between the two spaces between each individual molecule in 2D space or 3D space, okay? So volume is the macroscopic property, mean free path is the microscopic property. The last macroscopic property that we need to know is temperature, usually in the units of Kelvin. We just need to know that degrees Celsius plus 273.16 Kelvin is equal to degrees Kelvin, okay? For the conversion of the temperature from Celsius to Kelvin. It's rare that you're gonna have to convert from Fahrenheit to Celsius, but yeah, you don't need to worry about that. It's mostly gonna be in degrees Celsius, and you have to convert it to degrees Kelvin. because it's always in some unit of degree Kelvin. And we know that microscopic property for temperature already, that's the average kinetic energy. Okay. So much so we know that kinetic energy was what? 1/2 mv squared that we have in our system. So here's a look at those macroscopic properties, the pressure, the volume, the temperature that we look at when we're dealing with gas laws and ideal gas laws. And this is what's happening at the microscopic scale. One's creating collision forces. It's a number of molecules of gases colliding with the side walls of the container to give you what we call pressure, or the number of molecules colliding with your object above it to exert that fluid pressure that we talked about. Volume on the micro scale is just simply the distance between the molecules, and temperature on the micro scale is just the average kinetic energy. Is anyone else having that problem?
Yeah, it just says started screen sharing. Okay, I'll sign off and reload.
Yeah, is anyone else having that problem? Okay. Yeah, I was like, I think, yeah, sorry about that, Phyllis. But yes, hopefully someone can screen cap this for her or take a screenshot and then you can share it with her when she comes back in. If not, she can email me as always for lecture notes. So this is the macroscopic versus microscopic properties for gases. So let's take a look at how we can take that temperature. Let's go back. So that temperature that we're talking about, we know that temperature is directly proportional to kinetic energy. So we know that that's the kinetic energy is 1/2 mv squared, and the temperature is proportional to the internal energy of the gases, which is 3/2 RT, right? And so if we want to solve for that speed, we can see that speed, can you see it now, Phyllis? We solve for this. It's going to be the square root of 3RT all over the mass, right? Or the molar mass in your system. Awesome. Yeah, I apologize. I don't know why it didn't show originally, but I've been using the whiteboard the whole time. So this is commonly referred to as the root mean square velocity. So it's root mean square just means the average velocity of those molecules that are traveling due to the temperature of the gases. And this is the microscopic level of what's occurring for every gas molecule. So you know that these are all equations that you've dealt with before. Internal energy of a gas, we did that in thermodynamics. Kinetic energy in the work and energy lecture. Forces, change in momentum, this is from impulse. Pressure is force per cross-sectional area. We know that from our fluids lecture, okay? All right, so now let's compare real gas behavior versus ideal gas behavior. So let's look at gas behavior and when we're gonna have what being applied for our ideal gases versus our real gases. So let's first look at ideal gases. So for ideal gases, we make a bunch of assumptions. The first is that the particles have no space or occupy no volume, right? No space means no volume. So that means everything is a point mass. 2, perfectly elastic collisions. So all the collisions that we have with every molecule is conserved. So kinetic energy between the collisions are conserved. So none of the energy is lost during the collisions when we have an ideal gas. The third thing, we have no IMFs, intermolecular forces. So no dipole-dipole interactions, no attraction, no repulsion. This is for ideal gases. And last but not least, ideal gases obey the ideal gas law. PV equals nRT. And this is the combination of all the work from all the scientists that put it together. And we're going to go over each one of those experiments. The only thing that we need to remember is for gases. So the universal gas constant R is 8.314 kPa times liters per mole Kelvin. Yes, this is one of those things that they expect you to know. And it's going to be 0.00821 when you have atmospheres, liters per mole Kelvin. So depending on whether pressure is given to you in the normal sense with pascals or in the atmosphere sense. So you remember using this number a lot in general chemistry in your chemistry passage. You remember using this number a lot when you're doing physics, right? Yeah, you did the second one because you're doing chemistry. But when you're doing physics and thermodynamics, you use the second one, the first one quite a bit. Yeah, the second one is only when you have atmospheres as your pressure, okay? So just remember that pressure is in the units of atmospheres. All right, so that's ideal gas behavior. Let's take a look at what happens when we have real gases. So with real gases, we're looking at van der Waals equation, but first thing we need to know, molecules interact, right? And in doing so, this alters the pressure that you have in your system. So A is defined as the attraction coefficient so if A is greater than 0, the molecules are going to attract. And if A is less than 0, they're going to repel from each other. So what we notice is that the observed pressure is the ideal pressure minus that attraction coefficient times the number of moles all over the volume that you have for those molecules. Okay. So notice that when they attract, P observed is going to be less than P ideal because there's less molecules to collide with each other. So less collision force or collision frequency. And if they repel from each other, we notice that P observed is going to be greater than correct. Sorry. Sorry, trying to fit it all on one slide. We have a lot to go over today. So P observed is going to be less than P ideal in this case, right? I mean, greater than P observed. So because the molecules repelling from each other gives you more collisions in the system. So therefore, increased collision force, increased collision frequency due to that repulsion of those molecules having dipole-dipole interactions or ion-dipole interactions. Okay. The second type of interaction that real gases have are molecules have size. What does that mean? There's this thing, this term B, I call it the bigness coefficient. So it's like the size coefficient. And it's always positive. Okay. This term is always positive. Okay. So volume observed is equal to volume ideal, which was no volume really, the minimum, plus the number of moles times that bigness coefficient. Molecules interact with each other. So when they collide, Michaela, they can either attract or repel. So in an ideal gas, they would collide with each other and they would have no attraction to each other. So in ideal and real gases, collisions still occur, but in a real gas, the molecules then interact with each other. And then last but not least, you have van der Waals equation. And realistically, we're solving for P ideal, so you get P observed added to the attraction coefficient times attraction or repulsion. I thought I spelled that out right after I wrote the attraction coefficient. Yeah. So when they say interact, I mean, like literally I wrote attract, repel. Sorry, I know you're probably like driving somewhere. So for V ideal would have been V observed minus NB. Long days, I understand. It's hump day, Wednesday. Yeah, sorry. I'm trying to fit everything in, so it's hard to put everything into sentence form. So hopefully you can write down what I say, and I'm trying to paraphrase it as best as I can to fit it on one single board so we don't have to keep on flipping through pages, because I have a lot to go through, because not only do I have to go through all the gas laws, Avogadro's, Boyle's, Charles, was it Dalton's, Graham's law of effusion, and Gay-Lussac's, right? We still have to go through all the phases and phase changes. I just think of it as the ABC of gas laws. That's how I remember it. A, B, C, D, E, and then G. There's no F. There's no dude with an F name. Okay, but it's easy to remember that way. Yeah, A is for Avogadro's, B is for Boyle's, C is for Charles, D is for Dalton's, E is for Graham's law of emissivity or effusion, and there's no F, and G is for Gay-Lussac. Mm-hmm. That's how I remember them. Okay, so let's go over the gas laws. So Gay-Lussac's laws takes into account ideal gas law. Sorry, someone commented that F is what you yell when you see a gas equation. To be honest, I'm actually yelling yay when I see a gas equation, because that just means it's going to be easy. I'm going to go over it, Phyllis, for the mnemonic, right? I literally call it the A, B, C, D, E, and G of gas laws, right? So A is for Avogadro's, B is for Boyle, C is for Charles, D is for Dalton's. These are all each a law, Phyllis. And E is for Graham's law of effusion, and G is for Gay-Lussac's law, which has to do with pressure and temperature. Okay, so let's go over Avogadro's law. So this is the A. So for Avogadro's law, we know that pressure and temperature are constant. I know, I'm hungry. I'm thinking of avocado too. I know. I still love that joke. A ripe avocado is like really rare to find, but when you have like 5 ripe avocados, then you got problems because you can't eat it all. So really, Avogadro's law counts thing he's known for, the number of moles, right? So V1 over N1 is equal to V2 over N2. This is a linear relationship. And it makes sense, right? So if we're adding more moles of gas to a system, we're expecting a large volume, right? You see that when you blow air into a balloon, right? Avogadro's law, pretty straightforward. I put in more gases, I get more volume, right? B for Boyle's law. For Boyle's law, temperature and number of moles are constant. So how do we fix the number of moles to be constant? We have a closed system. So the balloon, so to speak, is tied off, right? So what we notice is that P1 V1 is equal to P2 V2. And we know that this is an inverse relationship. We just know that as you increase pressure, volume will decrease proportionally and vice versa. Just realize that if you had a PV diagram, it'll look like so. And then if you had a higher temperature, everything will raise up. This is at a higher, so you know what's happening in the system. Still the same. It's because you're keeping the other side of the equation constant, right? Remember, these guys didn't know ideal gas law like way we know ideal gas law, right? They developed all of these things separately. You think of them as applying parts of ideal gas law, but like when they were doing their experiments, like you need to realize that there was no such thing as ideal gas law. It's the conglomeration of all their experiments together is how we got PV equals nRT, right? So you're thinking like, oh, why aren't they using R? Why aren't they using number of moles? Why aren't they using temperature? Well, they're keeping these things constant because they had no idea that they existed yet, right? They were just like, here, I have a closed fluid system. What happens if I increase the pressure by putting it underwater? If pressure increases, what happens to volume? It decreases, right? And if pressure decreases, then as the balloon rises, the volume expands, right? You get that when you're going diving too, right? Exactly, right? So that's why when you go deeper and deeper underwater, you feel like you're getting your lungs crushed, right? Because the external pressure is pushing harder and harder on you. Remember, we talked about that hydrostatic pressure from fluids. And as you go deeper and deeper, you have more weight of fluid pressure pushing on you, which is what's doing to this closed fluid system. Your lungs, right? Your breathing, you are just a gas bag when you're underneath the water, right? And so that pressure is pushing on you and it's forcing your volume to decrease in the system. So gas lowers, right? So then there's an addendum and a sub-law that happens when you're diving, and that's called Henry's law. So let's go over Henry's law. Henry's law states that the increase in pressure leads to the increase in amount of gas that dissolves in solution. So scientists have actually looked at this, and if you think about it, this is what's leading to the bleaching of coral reefs. Because of the increased CO2 in the atmosphere, that increased pressure of gas due to our global warming and using of fossil fuels and using combustion reaction through driving, through factories, through power plants, burning coal, trains, like, anytime we burn something like those natural fossil fuels releasing carbon dioxide. As that pressure of carbon dioxide is increased in the gas medium, that pressure is now pushing down onto the ocean. And Henry's law states that as we increase the pressure of the gas, that leads to the increased amount of gas that dissolves in solution. So what happens when carbon dioxide dissolves in water? It forms carbonic acid. So that acidification is what's bleaching the coral reefs. And so you see the coral reefs begin to die because of this extra acidification of the water, the oceans that we have. And so a lot of species of plants, because they use the coral for as homes and food and all that stuff, are beginning to die. So we're getting less diversity. Mm-hmm. Yep, less seafood out there. And it's really sad. Henry's law, we also used it all the time, right? Anyone had a Coke? Right? Oh, there's less seaweed out there too, right? Because of this extra acidification. Yep, less nori. Everyone suffers, I know. Vegans and pescatarians alike. But yeah, so what happens to the gases? So this is happening in the alveolar exchange. This is Marissa's right. So as you dive deeper into the ocean, what happens? The nitrogen, the oxygen gets dissolved into your bloodstream, right? So those gases that we have, as they're getting compressed, right? The volume of gases is getting compressed as the pressure increases on the outside of you. You're feeling this like compression, and you feel that increased pressure. The gases inside your lungs, right? The nitrogen, oxygen, carbon dioxide, they're all getting compressed, and that increase in pressure that you feel is now pushing those gases into solution, right? And so now you have gases inside your bloodstream. Correct. Someone mentioned that this is why you need to rise slowly as you go back from diving, right? If you rise too quickly, those gases come out of liquid phase from gas phase, kind of like you opening a bottle of like Coke or a 2-liter bottle, right? What happens? All that gas that was pressurized into the system comes out as bubbles. Imagine that happens in your blood vessels, in your capillaries, in your arteries, arterioles, right? So anyone that, if you never felt that pain, like I'm sure everyone's felt this pain, right? You ever stop peeing midstream because like, family member walks in, significant other walks in on you, and you're just like, what are you doing? Right? That's how it feels like, except everywhere in your body. Not just like at your ureter. So imagine that rapid expansion of your ureter that you're having when you stop peeing midstream, right? Imagine that's happening to every blood vessels in your body. So that's why this is super painful, and you'll start writhing in pain. Like most people this is called the bends. And when you're diving, you need to like equilibrate the gas pressures and have them come out in your lungs, not in your blood vessels. So if you come up too quickly, right, like you see a great white when you're diving and scuba diving, and that leads you to like just book it up right to the top, that's going to lead to the bends. So then what happens is you have to go into a hyperbaric chamber or high pressure chamber to push all those gases back into solution. So then it slowly decreases the pressure over time so that those gases come out at the alveolar exchange, like Marissa talked about. So all of this is very practical and inside the body as well, right? And this is because we are a closed system, especially if we're diving, right? Any questions on that? The when you go up really fast, you change pressures really fast, right? So if you decrease the external pressure, what happens? The gases that were pressurized to be in liquid solution come out of solution, right? So think of a 2 liter bottle, Michaela. When you first, before you open your 2 liter bottle, can you squeeze it? No. Why? Because it's rock hard. It's pressurized, full of CO2, right? We call it carbonation, right? Same thing with your like Coke cans, right? If you ever try to like open your Coke cans and try to squeeze it before you crack open the lid and you hear that, that's just all the gas is coming out of solution, right? And coming out through that small hole. Because you decrease the external pressure, you allow an avenue for that gas to escape. Now it's allowing the decreased pressure, the decreased external pressure that's pushing on the liquid allows for the gases that were in solution to come out of solution and go become bubbles. So going up quickly reduces that external pressure. So yeah, this is something that happens all the time, right? Every time you drink like a bubbly drink, every time you have Alka-Seltzer, every time you have any of those like in Hispanic countries, when I travel to like South America and go to Central America, there's always agua con gas, agua sin gas, right? So you always are taking about, yeah, everyone's like La Croix. I love that sound. It's just like, sometimes carbonation is good, right? Because as you get older, you'll find out that this is why your parents always drink things with gas. They always like some champagne or some mimosa or something, right? It aids in digestion, right? Because it helps break the food particles apart. Your stomach gets weaker and your muscles get weaker over time as you get older, especially if you abused it by doing all these like eating challenges that Americans do, right? Eating too much, eating too much fat, eating too much whatever, right? And so if you eat a lot all the time when you were younger, your stomach muscles and stomach lining get weaker. And then as you get older, it doesn't want to do as much like compression to break the food apart. So when you drink gases in there, the bubbles coming up help break the food apart. Everyone loves their carbonated drinks, especially Americans, right? Everyone has their own soda stream at home now. But yes, this is what carbonation is. This is the application of Henry's law. Okay. So the bends and carbonation are just application of Henry's law, where by increasing pressure, you dissolve more gases in solution. Okay. And it's a little addendum to Boyle's law. When you have a closed fluid system, increase pressure, decrease volume, decrease pressure, increase volume. Okay. The next part, so we had the A, B, and now we're going to do the C. C is Charles' law. So with Charles' law, number of moles and pressure are constant. So the way I remember it, I had a roommate in college, no joke, freshman year. This guy was like econ major, and he was like, "Oh man, life is easy. Taking econ." Literally didn't leave the dorm room. Read his books, stayed in the dorm room, watched TV all day. So I always remember it that Charles was in charge of the TV, which is temperature and volume, right? That's how I remember Charles was always in charge of the TV. So Charles' law has to deal with temperature and volume. So volume over temperature is equal to volume 2 over temperature 2. And we know this is a linear relationship, right? And you see this if you ever leave any helium balloons in your car on a hot day. So as the temperature increases, what happens to those balloons? You're telling me you've never had this happen. Come on. Out of all your birthday parties and stuff like that. Oh man, Charlie and the Chocolate Factory. Everyone wants that golden ticket. But yes, what happens? Increased temperature, increased volume, right? Uh, yeah, I was asking what happens to the balloons on a hot day inside your car, right? Increase in temperature, increase in volume, the balloons usually pop. Yep, they expand, right? Increased volume, expansion, and usually to the point where they pop, right? Yeah, so when I say linear relationship, that means that if I increase temperature like by a factor of 2, I increase volume by a factor of 2. Equal amounts. And then so when I say inverse relationship, I mean that when I double something, the other one gets halved. Okay.
I just mean like, so like when you say, are you saying that V1 and T1 are linear, or is V1 over T1 linear to V2 over T2?
Oh, so V1 and T1 are just the volume and temperature at one state, right? And so V2 over T2 is the volume over the other state, but that ratio is always going to be constant or equal to the other state. So then when you increase one, you increase the other, respectively. Like you T1 and V1 are proportional to each other. So when you increase them, like V2 and T2 would be another set of new volume and temperature. They would still be equal. Okay. So when we talk about it with ideal gases, you think of volume and temperature as a simple linear, right? But this is for ideal. But for real, you're going to have different linear components at different states for volume and temperature. So it'll look like this. This is your melting point. It'll look like slightly different slope. And then another slope for your boiling point. So this is your solid, liquid, and gas phase, respectively, right? For your vapor pressure that's in solution, right? For gases that are in solution, okay? So we're going to skip over D real quick. We'll get back to D, and we're going to go over Graham's law of effusion. So E is next, okay? So that was Charles's law. Graham's law of effusion. So we'll look at gas movement. So we can talk about effusion, infusion, and diffusion, right? So the way to remember gas movements, gases edify us, right? They teach, right? So there's EDI. So there's effusion, diffusion, and infusion. So effusion is gas moves in from the outside through a pore. So that's effusion. So gas going to the outside, from the inside to the outside through a pore. Diffusion is gas moves from high concentration to low concentration. So usually direction dependent. And infusion, gas moves from outside to inside through a pore or an opening. Okay. So when we talk about gas movement, so EDI, they help teach us. There's no F and Y, sorry. That's my mnemonic to help remember how gases move. They edify us. So Graham's law of effusion simply takes the fact that we know. How is E different from E above? They're the same. Graham's law of effusion. What other E are we talking about? We're talking about this E. I is infusion. It's direction dependent. One goes in, one goes out. Think about it. When you effuse, when you infuse, make sense? You're sucking in gas. One goes from the inside to outside through a pore. The other one goes from the outside to the inside through a pore. Inhalation, exhalation. No worries. Graham's law of effusion. So we know, remember, we use our root mean squared velocity, V root mean squared, square root of 3RT all over the molar mass, right? Capital M was our average velocity that we had earlier. So what Graham's law of effusion does is he takes into account whether it's for temperature or for mass, molar mass of the system. So V1 over V2 is equal to the ratio of M2 all over M1, or the square root of T1 over T2. So this is when T is the same. We can compare the ratio of the masses and how they move. And when this is when the mass is the same, so the same gas, we can compare the different temperatures of the gas and how well molecules move through that gas and how greater the movement of those molecules are. This V here is the velocity. And we use this when we look at those like topics like isotopic enrichment. Like, remember all those, like when we talked about nuclear chemistry and how we separate the different isotopes like hydrogen, deuterium, tritium, right? The heavier the molecules, the less they move. The lighter the molecules, the faster they move. That's how we remember it. So Graham's law of effusion gives us a way to calculate those different gases moving through different pores, okay? All right. Last thing that we need to go over is Dalton's law. This is the D of partial pressures. Sure, I can go back. Cool. So Dalton's law of partial pressures. So Dalton's law takes into account that what we call total pressure is equal to the partial pressure of each of the individual gases in the system, right? So let's say we have 3 different gases in a container. So here's your container. Let's say we have helium, argon, neon, each at half a mole or half an ATM. Same diff, right? So the total pressure would have been the sum of all the pressures. We're going to have a valve stem. And when we lift it up, it opens it. When we pull it down, it closes it, right? So, and the total pressure, the total number of moles is equal to the individual number of moles of the individual gases. I just did 3 arbitrarily. You can have as many gases that you have in a typical gas environment, right? So you think about like what we call air is 71% nitrogen, 21% oxygen, then trace amounts of all the different gases in terms of noble gases in the atmosphere. Okay, so depending on all the different gases, you can have the total number of moles be the different total number of moles of each of all the individual gases added up. So what Dalton's law of partial pressures does, half an ATM of helium, half an ATM of argon, half an ATM of neon. That's what it says in the drawing. So if we were doing our Dalton's law of partial pressures, we can just simply take off and say that, look, every partial pressure that we have in the system means that the total pressure is going to be 1.5 atmospheres, right? We take the individual partial pressures of each gas, add them up, and we have that in the system. So to find the partial pressure of one gas, we can take what we call the mole fraction, XE. This is called the mole fraction. And that's simply the moles of that gas divided by the total moles that we have in the system and multiply it by a total pressure. So what Dalton's law of partial pressures does, it allows us to calculate for the pressure of each individual gas if we know the ratio of the moles of gas that we have in the gas phase or in solution. Okay. So this is Dalton's law of partial pressures. We take the mole fraction of one gas, we're going to get and multiply to the total pressure, we can get the partial pressure of that gas at any given point. Okay. Now, if you think about it, if I open this system up using Graham's law of effusion, which gas would come out first? Which one would be the fastest? Helium, neon, or argon? Why? I think Michaela has the right idea. Smaller molecules move more quickly, right? Heavier molecules have more inertia, applying the physics that we talked about, right? And are less likely to move in a system. Okay. So lighter masses have greater velocity, right? So remember, given the same temperature, they have the same kinetic energy in your system, or the same average kinetic energy. So the ones that are smaller masses have a greater velocity. The ones that have larger masses have a slower velocity. Very good. So that's Graham's law of effusion. So if I opened it up, you would know that that would go out first. So therefore, the mole fraction of argon would be the greatest and when we first open it out, right? Because there are going to be more moles of argon because both helium and neon are going to be moving out of the system at a greater rate. Okay. So we just gone over all the different laws. And so when we combine those laws together, Avogadro's, Boyle's, Charles, and Gay-Lussac, we get that combined ideal gas law, right? The combined ideal gas law, PV, P1V1 over N1 R1 RT1 is equal to P2 V2 all over N2 R T2. So if you combine all those guys together, we get this relationship. And this is where we get the ideal gas law coming from, right? This is what we call combined ideal gas law. Where we take both and all their combined experiments and efforts together. And this is where the ideal gas law came from. It didn't work the other way around, like how you guys learned it, right? You guys learned ideal gas law, and then you were like learned about all their individual like experiments. There was their individual experiments that led to the combined ideal gas law. Yeah, I was confused too. I was like, I remember I'm like, wow, these guys are idiots. They didn't know what, like, why didn't they just use the ideal gas law and just be done with it? Why are they like experimenting with, just volume moles or just temperature and pressure or pressure and volume? These guys are fools. Right? But without that work, you wouldn't have gotten an ideal gas law. Just saying. We all had it backwards. So that mistake that you made, Jonathan, I did that too. And I was just like, what the hell? These guys, they don't know what they're talking about. But yes, when I learned about it later and I looked at the history of when it was being done, these guys were doing this like about 100 years before the combined ideal gas law came about. So I'm like, oh wow, I feel so mean for no reason. Okay. I know. I felt like you just had that epiphany here. Okay, so let's take a look at your phases and phase changes next. So we're going to take a look at the definition, the difference between a gas, a liquid, and a solid. We're going to look at all the 3 phases that you have to know for your MCAT and the 6 phase changes that you have to know for your MCAT as well. Okay, we'll look at phase change diagrams, both standard and the phase change for water. We'll look at heating curves. We'll look at the vapor pressure theory coming about from Clausius-Clapeyron equation. And we'll look at the colligative properties of liquids as we add salts into solution. Okay. So phases and phase changes are next. So we discussed gases. So gases, or being in a gas phase, is just one of the phases that we have for physical properties of materials. So there are 3 phases. The first is a gas phase that we've just gone over. So gases have no definite shape or volume. They are typically the highest energy and entropy. S is your entropy. So most disordered. B. Next, in terms of order, are your liquids. So liquids have no definite shape, but have definite volume. And they usually mold themselves to the volume of whatever the container is. Okay. And last but not least, solids have definite shape and volume. So solids have the lowest energy and entropy in the system. The reason being, it has that having that definite shape because it forms a lattice, right? And we see that when we were looking at the solid state structures of things from what we talked about last week and Rutherford's experiments, right? Having that nice structure and to create that lattice structure, okay? So the next diagram I like the most, we have gas phase, we have solids, and then we have liquid. So many things are happening here. So to go from a solid to a liquid, what do we have to do? Sure. I didn't write a lot in the last one. Sorry. That's why I moved relatively quickly. Solids have definite shape and volume, right? Liquids have no definite shape but definite volume, and gases have no definite shape and no definite volume. So, yes, we're breaking. Are we really breaking bonds? We're breaking lattice structure. I guess that's considered bonds. They're intermolecular bonds, right? So someone said that we're breaking bonds to go from solid to liquid. Yeah, we are adding energy. That is correct. So this is an endothermic process, right? This is an endo. We're adding energy to go from a solid to a liquid. What's this? What is this process called? Good. Someone wrote changing phases. Wow. Yes, that this specific phase change is called melting. Thank you, Michaela. Okay, so we had to add energy to melt something, right? What about going the opposite way from that liquid to go to a solid? This is an exothermic process. We're giving off energy. By the way, the energy associated with this is the delta H of fusion. Yeah, we're talking about freezing or fusion. Okay. What about to go from a liquid to a gas? So we got sublimation, we got evaporation. Evaporation is what we talk about when we go for water to liquid to gas. But what's the general term for any liquid to go to a gas? By the way, this is endo because we're going to require energy. Boiling is the process that we go to get there. What is it called? To take something and make it into a gas phase, from a liquid to a gas phase, the general name for it. Correct. Vaporize. So this process is called vaporization. And to go from a gas to a liquid, this is an exothermic process. You're giving off heat. Correct. We have, and you guys see it every morning on your windowsill, condensation. Okay. The delta H to go from here to from liquid to gas is called the delta H of vaporization. Now, what about going from a solid to a gas? What's this process called? We know solids are most stable, gas are most unstable, so we know that this is definitely an endothermic process. Someone has said it before. Not deposition to go from solid to gas. Sublimation. This is now sublimation. I believe Michaela had said sublimation earlier. But this is sublimation. Right? This is when your dry ice becomes gaseous CO2. Right? By the way, that's what dry ice is solid CO2. I'm sure you guys used it plenty of time in like plays and whatnot to make correct. So Marissa had said it to go the other way. This is an exothermic process. It's giving off heat. And this is called deposition. Correct. Some other people had said deposition is the other way. So you hardly ever see deposition unless you're like making, wafers and making microchips and stuff like that. You hear about that process all the time, where you go from a gas to a solid. And you're depositing the solid phase onto that thin microchip wafer. Okay. So this delta H is called the delta H of sublimation. Okay. So one's positive, one's negative, but literally you're doing that. And what you need to notice is that the delta H of sublimation is the greatest amount of energy change because you're going from the lowest energy to the highest energy state. The delta H of vaporization is next, and then the delta H of fusion is the smallest. Because if you're breaking up something in terms of fusing, you're only breaking the intermolecular bonds of those molecules from the lattice structure, right? You're only breaking the lattice structure up to go from a solid to a liquid. And then because the IMFs are still there, you still have to break those up to go from a liquid to a gas for your delta H of vaporization. And to go from a solid to gas, you're literally making that big jump together for melting and then for condensation. I mean, for vaporization as well. Okay. So let's go over some thermal chemistry terms as well, since we're here. I think we went over it before. Let's just make sure that it still sticks. Isothermal. What does that mean? Constant what? Temperature. Isobaric. Constant pressure. I'm glad you guys remember it. Isochoric. Correct. Constant volume. And adiabatic. Heat loss is 0. So no heat loss. Heat is constant in your system. Okay? Cool. So everyone still remembers their thermal chemistry terms and thermodynamics terms that we talked about. Technically, all of these are considered closed and they're done. So for the first three, isotherm, isobaric, and isochoric are done really, really, really slow because how are you going to not change volume, right? When you're compressing and expanding something, right? To keep the volume the same, it's not possible, right? So that's why isothermal, isobaric, and isochoric are ideal, and adiabatic is like the only real one. They're all technically close. So let's look at the phase change diagram. So this is your standard diagram. So where's your phases? Solid, liquid, and gas. Left something out that's kind of important. My axes. Need to know your axes. You can't label anything, and I left it out on purpose. These generally are typically in pressure and temperature. This is usually in Kelvin and usually in atmospheres or kPa. Usually in atmospheres for pressure, right? So this is your solid plus vapor, because at any temperature, there's always going to be having some amount of your liquid evaporated or vaporized in solution. And the bottom is gas. There are some points of interest on a standard phase change diagram. The first point here is where all those lines connect. This is commonly referred to the triple point. At this point, all three phases exist. You guys go on YouTube and look up triple point and check out some videos. You get to see an object be solid, liquid, and gas, and they change based on the fluctuations of temperatures around it. Wow, you're good. That's good. I will go easy on the gummy bears. Someone recognizes the chewing of gummy bears. That's amazing. Like, my camera's not on, right? Yeah. The next point that we care about is the maximum point here. This is referred to as the critical point. This is the last point that we can't tell the difference. Between a liquid and gas. Anything above this is the fourth state of matter. We call that a supercritical fluid. Fourth state of matter is usually called plasma. But for you guys, since it's so hot and it's so high in temperature, it'll never be discussed inside the human body. Okay? So you don't have to worry about it. Like, we're talking like magma, lava hot, right? To get the supercritical fluid or super high pressures, enough that most cells would like collapse under that increased force from the external environment. Okay, so those are the two key points that we need to know for a standard phase change diagram. So my question to you guys is, name the phase changes. So this is A, we'll call that vertical arrow going down. Yes, so that is a big if. We would need to have a bunch of mutations, and our skin wouldn't need to be porous, right? And we'd have to be fairly dense. But yes, if we can survive those extremes, we'd be a supercritical fluid. We'd be plasma. So name these phase changes on this phase change diagram, A, B, C, and D. You have all the necessary materials. So A is going from a solid to a liquid. At constant temperature. That's right. Solid to liquid is melting. What type of melting is it? Be more specific. Keep in mind all those blue lines are horizontal or vertical. Think of all those processes that we just went over. Thermal chem processes. Yeah, right? What's not changing here? Temperature. So it's isothermal melting. B, what's happening here? Going from gas to liquid. What type of condensation? Iso what? Good. Isobaric condensation. What about C? Iso what? You're going from solid to gas. Good. Isobaric sublimation. And D, last but not least, we know this is an isotherm. Going from a gas to a solid. Isothermal what? Deposition. Excellent. Good stuff, guys. All right. So that's your standard phase change diagram. Let's look at the one that's weird. So this is the phase change diagram of water. Pressure, temperature, degrees Kelvin, look like this, like that, and like that. So this part right here is where it's weird, right? Right, everything has a positive leaning slope for all standard phase change diagrams. This one's different. So for water, remember how I told you guys? Water is most dense at 4 degrees Celsius when I went over your specific gravity equation when we did fluids. The reason being, what happens as we increase pressure on water, going from a solid state to a liquid state, right? As we increase pressure, what do we notice? It goes from gas to solid, right? It deposits, and then it becomes a liquid, right? So water is most dense at 4 degrees Celsius, because remember, solid water floats. It's ice, right? So it's less dense than water itself. Keep in mind that when we apply pressure on water or on ice, that force per cross-sectional area gets ice to melt, right? So just in case you guys go to a place where they have frozen lakes and frozen ponds and you're not used to that, what do you do if the ice cracks? If you hear the ice beginning to crack, what do you do? Very good. Why, Sophie? Using this equation in physics that we've learned. P is equal to F over A. What does laying down do? In terms of pressure is equal to force over area. Yep, increasing area decreases pressure, right, in your system, making it less likely to crack more. Okay, so just keep that in mind. But yes, water is weird. It's the only one that goes from, as you increase pressure on it, it'll go from solid to liquid. Everything else goes from gas to liquid and so on and so forth as we increase pressure, and gas to solid as we increase pressure. But it's the only one where the solid then becomes a liquid, and that's because of its phase change diagram. Belly crawl out of there. Ideally, you yell for help, they throw a rope, and you just lay there. But if there's no one around, you belly crawl, like, you know, like a walrus. Now you think about it, you might be looking ridiculous like a worm in a walrus, but you'll be a live worm as opposed to a frozen popsicle. So, no shame if I can live. Right? You can laugh about it later. All right. The next thing we need to know are heating curves. Curves, not carves. I don't know why they call it heating curves, because it's actually all straight lines. So the y-axis is temperature in Kelvin. The x-axis is heat that we've added to the system. And it looks something like this. This temperature, it's the temperature for the melting point. This temperature is the temperature for the boiling point, or for vaporization, right? So on this heating curve, as we add heat, we're changing from solid state to liquid state to gas state. And in between, we have this solid to liquid transformation, this liquid to gas transformation, right? Here we're applying delta H of fusion. Here we're applying delta H of vaporization. And for each one of the solid, liquid, and gases, we're applying Q is equal to mCp delta T, right? And if you want T by itself, you solve for it by itself as a function of Q that you're added to the system. Yep. That's how you guys like to remember it. Q is equal to MCAT. And the units are always in joules for each of these systems, except each one has its own heat capacity, right? This is the heat capacity of steam. This is the heat capacity of water. And this is the heat capacity of ice. Okay, for each of the different phases of solid, liquid, and gas, respectively. And I say that you're going to only deal with the liquid version, solid, liquid, and gas form of ice. They would have to give those numbers to you for different heat capacities. to calculate these heating curves. Any questions? So if we rewrote it, it would have been delta T would have been equal to Q over MCP, right? Where Q is your x-axis, and we rewritten it as 1 over MCP times Q. This is your x, this is your slope, and this is your y, respectively, right? For the change for each of those slopes that you had in your system. Yeah, this is a 1. Any questions? This is the heat added. Okay. So the next thing we need to know is phase change theory. So we talked about all the different types of phase changes. Now we're going to take a look at phase change theory and what's happening. So as that liquid goes into gas phase, part of it at a certain temperature is always going to be in some liquid phase, right? So what we call vapor pressure is the force per cross-sectional area exerted by liquid vapor coming off the surface. Of liquid. What we notice, if we graph vapor pressure as a function of temperature, there's always some type of vapor pressure unless we're all exactly at absolute zero, okay? And what we consider boiling point, or the temperature for vaporization, if this was water, that would be 1 atmosphere, okay? So how do we get boiling, or how do you get something to boil, right? Whatever that something is, when it's boiling, the vaporization pressure that we have from that liquid becoming a gas is equivalent to the atmospheric pressure. So keep in mind there's gas molecules pushing down on this liquid. So when we have boiling, the amount of liquid coming up is equal to the equivalent to the amount of gases that are pushing down. Okay? So when boiling, P vape is equal to P ATM, which is why when you go to higher elevations, you boil a lot sooner because your pressure for vaporization is reduced, right? So if you go to school in Colorado and live in Denver, right, you're going to get your water to boil a lot faster, right? Because it's at a lower pressure, which means what? It's also at a lower temperature, okay, in your system. So remember that the only way to make something greater, so if we increase the atmospheric pressure, we increase the boiling point or the temperature for vaporization, right? This is pressure cooking. So anyone that have an Instapot? If not, I'm sure your parents do, right? There's a whole like culture around it, especially with parents nowadays. Everyone has an Instapot, right? Because all those like delicious stews, instead of slow and low, we can do it high and fast, right? Instead of wasting electricities for like the whole day in your slow cooker, you can do it at a much quicker pace because you're cooking at a higher temperature, right? That's how you get all that collagen to break down and becomes nice and soft. You didn't add the right ingredients. Someone said they made pho in an Instapot. I cook Instapot pho like maybe once every month. We'll talk about that. We'll talk about the recipe for Instapot pho. I'm Vietnamese and I love pho, so like pho is my jam. I can eat that like every day. Will do. Email me. I'll give you the Instapot recipe. So now if we decrease atmospheric pressure, like go to higher elevation, we'll decrease the boiling point as well, right? So if you were in the wild, anyone watch Top Chef? Remember that season they went to Colorado and they were in Denver and they were in the really high elevation? Went to that ski resort. They couldn't get the things hot enough to make stew. The meat never cooked. And the collagens didn't break down. So people had to like leave. The third thing we know is if we add solutes to solution, this increases boiling point. Due to colligative properties. What does that mean? So what happens when we add solutes to solution? We get things to break down. These salts break down. And two things happen. You decrease the surface area of the liquid and gas phase because the liquid now forms a solvation bubble around each of the solutes that we have in solution. So your salts will have all those water molecules binding around it. And because of that, we have a stronger IMF, intermolecular forces, right? Stronger IMFs mean what? More energy is required to break those intermolecular forces and get the individual water molecules to go from liquid phase to gas phase, okay? So when you add salts to solution, you increase boiling point, but what does it do for melting point? It decreases melting point because solutes disrupt the lattice structure. So in order to form a solid, you have to form some type of lattice, either crystalline or network covalent or some type of lattice, right? And so what happens is these big salt atoms that are charged start disrupting that lattice. Exactly. This is why when you go to really cold areas, you throw salt on the ground, right? What does that do? It decreases the melting point. So it doesn't freeze at a higher temperature, it freezes at a much lower temperature. So typically when you salt the ground or you salt your driveway, it melts the ice. Yes, it decreases the freezing point, right? Which means what? Ice will melt at a higher temperature, right? Even though it's below freezing for water, right? It'll still melt because of that. Anyone ever make ice cream from scratch? Sure. Sorry, someone wanted to go back to the slide with the for water. Yes, you would add salts into your ice, get the ice to melt, and then you would have that surrounding the chamber where you're churning the cream. And that makes it colder and colder, and you keep on adding more and more ice, and it gets colder and colder so that eventually that cream can churn and it'll begin to freeze, right? whether it's like bananas, strawberries, whatever you've made ice cream from scratch. Like you use heavy cream, use whatever flavoring you want. You'd probably drop in a few drops of vanilla, right? It melts at the higher temperature, but the freezing point is at a lower temperature. So it won't freeze until it gets to a lower temperature. Okay. What did Zoe say? Oh. She said she was in your class? What? That's crazy. And you guys met up with each other after? That's crazy. Crazy talk. Small world. 6 degrees of Sophie. Okay. So we'll go back. You can get rid of all those Avogadros, Boyles, Charles Laws things. And I need to go over your change in boiling point temperature. Actually, before we do that, we can do that right here. The change in temperature of that boiling point is equal to K times I times M times gamma. So where K is the constant for solvent, for water, 0.51. Okay. I is the number of solute particles. M is molality. And gamma is the activity coefficient. For the solute. NaCl in water is considered 1 for the activity coefficient. But this is the equation that governs that boiling point elevation. So to sum it up, colligative properties lead to boiling point elevation and melting point depression. Stronger IMFs mean higher boiling point, right? And because of having those salts in solution and them disrupting the lattice, it causes you to have a lower melting point. So stronger IMFs lead to higher boiling point. Solutes in solution disrupting the lattice leads to a lower freezing point or melting point. Yes, molality is little m. Sorry, I was trying to write it really quickly. Cool. That's crazy. I can't believe that after all this time, you just realized that Zoe was in your class. Middle school. Okay, let's delete this. Next thing we need to talk about is the practical application or for the experimentation that we have here. And that's taking a look at distillation. And any chemist worth his salt always has a still, like no joke. Chemists like making alcohol, no joke. So distillation takes advantage of the liquid to gas phase transformation. Takes advantage of different boiling points to separate and purify two liquids. So if we know that we have two, given our vapor pressure, two different types of vaporization curves. This is temperature in Kelvin. This is the boiling point for molecule A. This is P vapor of A. This is P vapor of B. And this is the boiling point of B. So, how distillation works? We usually have a container that has both solutions or both liquids in solution form. We're going to heat it up. We're going to get that gas molecule to rise. Then we can condense it. And I'll be sitting in some type of ice bath. These are supposed to be ice cubes. Right? And you get all those like individual molecules to recondense. So what ends up happening, so if we look at it here, P vape of A versus P vape of B, right? Looks like A compared to B in gas form is equivalent to 4-to-1, right? It looks like it's 4 times as large. So after going through one distillation, you have 4 A molecules for every 1 B molecule, okay? Now, if we do this again, we'll get a 16-to-1 ratio. We do it again, we get a 64-to-1 ratio. We do it again, we get a 128-to-1 ratio, right? No, 6 carry the 196-to-1 ratio. So each time we do it, we're getting more and more purified of A, right? Pressure. This looks like this tall. This looks like it's 4 times as big, correct? In terms of vapor pressure, right? If remember using Avogadro's law, the more volume, the more pressure you have, the more moles you have of something, right? So distillation, did I do my math wrong? It's 4 times 6. Yep, 256. Thank you. Glad someone's paying attention. Cool. Yeah, so you're just multiplying it by 4. So 256. So it's just getting more and more purified, right? Hence why the more distillation processes that you go into, the more pure your alcohol is, the higher the cost, right? Because energy has to come about from heating this, right? You have to put in heat either through burning of natural gas, coal, fossil fuels, I don't know, electricity. You're heating it somehow, and that is taking up energy. So every time you do it, you get more and more proof or greater percentage of alcohol, right? At certain points, it's like a diminishing returns to go for this extra amount, right? You're getting like moonshine versus like extra moonshine at that point, right? Because if you think about it, 4-to-1 would be 80% alcohol already, and that's like 160 proof. So it's generally good enough for most of your alcohol content that you get from all your hard liquor. So this is the application of that, right? You think about this 4-to-1 ratio is 80 proof or 160 proof, which is 80% alcohol, right? Because you think about it, alcohol is lighter, it's going to be more effervescent, more volatile, and it's going to leave right? Because it has a lower boiling point in your system. And remember, when we talk about volatility, it's the ease at which something vaporizes, right? So when you say that you have a volatile chemical, it just means that it's going to go from liquid to gas phase easier. So just keep that in mind. Okay. So what we have to look at next is they would probably give you some data like a graph or with numbers, Sophie. So in terms of like a data table that would give you the thing. So what the question was asked was really good. How do you know that get that 4-to-1 ratio? They either give it to you in graph form or they give it to you in data form from a data table. So yes, I just drew a graph and it looked like it was route 4. So Raoult's law takes into account when 2 or more liquids in solution the vapor pressure depends on the mole fraction of each. So Raoult took Dalton's law of vapor pressures, right, where we know that the vapor pressure of 1 is simply the mole fraction of 1 times the total pressure, pure vapor of A pure, which is by itself 100%. So we're taking our mole fraction and doing that comparison. So he linearized it. So let's say on one side, we have 100% of pure A and 0% of pure B. And on the other side, we have 0% of A and 100% of B. So based on your initial conditions that you have in each, let's say that we have P vape pure A is 100 torrs and P vape pure B is 50 torrs. So you can know, let's say this is 100 and half of that is 50. Okay. So they found a linear relationship between the two using Raoult's law, using Dalton's law of partial pressures realistically. And you can add up each of the individual partial pressures to find the total vapor pressure. Based on the mole fraction that you have. So the pressure here plus the pressure here gives you that pressure there. Make sense? And so based on this linearization of the mole fraction of each of the molecules that we have or in solution, from 100% of one to whatever, and then you can figure out your percentages based on your molarity of how much you put into the system. You can figure out the vapor pressure that you have. That's what Raoult's law allows us to do. So based on the mole fraction of A and B relative in solution, you can figure out what the solution can be. Most of the time, they're just going to give you like a percentage, right? So in this case, you can see that this is like some percentage of A, and this is some percentage of B, right? Let's say that's like 63% A, and this is like 37% B. And so you can calculate the vapor pressures of each by knowing that there's a certain mole fraction of each to get that. And then you can add those two vapor pressures up using this equation to find the total vapor pressure. Does that make sense? That was an example. I just didn't put numbers to it. Sorry. All right. With that said, any further questions? So then we just covered our gas laws, ideal gas law, real world gas law, your van der Waals equation. You covered your Avogadro's, Boyle's, Charles, Dalton's, and Graham's law of effusion. Then we went over the 3 phases, solid, liquid, and gas, and the 6 phase changes, the different thermal chemistry terms associated with those phase changes, looked at phase diagrams, heating curves, and looked at vapor change theory by looking at how the external pressure of the gas affects the vapor pressure of the gas, and how solutes in solution change the boiling point and melting point, right, through the colligative properties. And then by using your phase change theory, you can apply it as an impractical experimenting for making, I generally do it for making alcohol, right? To separate and purify your alcohol to make it like higher proof. And Raoult's law takes into account that Dalton's law of partial pressures so that we can calculate at any given point, given 2 liquids in solution, the total vapor that we have in the gas phase from that due to the mole fractions of each based on this linearization that he has in his scale. Okay. All right. So let's see if I can give you guys a question. Let me open it up first, and then I will share it with you guys and give you guys a passage for the week. Okay. This is pretty practical. Yes, we went over a ton of stuff today. Apologies if like I was going a little too fast. I tried to go slow and explain everything in detail as much as I could, but we covered a ton of material. Okay. So if you have questions, feel free to come to office hours on Thursday from 12 to 2. Otherwise, I'll get you the passage so you guys can start. It's a ventilator passage. There's 7 questions. I'll give you guys 8 minutes to complete it. Time is up. Let's go over, I'll give you the answers. We don't have time to go over all the answers today just because I have a meeting at 4 that I have to go to as well. Sorry. But I can do this during office hours if anyone has questions on how we came about to these answers. 8 is B as in Bravo. 9 is A as in Alpha. 10 is B as in Bravo. 11 is D as in Delta. 12 is A as in Alpha. 13 is C as in Charlie. And 14 is A as in Alpha. Okay. So let's go over it again. B, A, B, D, A, C, and A. Okay. We have questions. I'll see you guys during office hours. Okay. We'll do it in office hours. Sorry, like I actually have another one to go to. But yes,